One rule you have seen in previous lecture, just going through this again. So rules of orientation. You have seen the orientation. Orientation is dependent upon what? If you remember, if you have already a group present on aromatic system present, then the new electrophile depends upon the nature of this group present. If let's say one or more than one are present, if one is present, you have seen in the previous this slide, we can classify them into two major categories. One is orthopara director, another is meta director. Which is orthopara director, which oriented is to ortho and para both. One is alkyl group if present, which is uh, electron donating to some extent, halogens and nitrogen, oxygen, phosphorus, sulfur, if present directly to such aromatic system, then they are orthopara director. But if we have some other groups like you have seen previous, so they are meta directors. This is when we have only one substituent. But if we have more than one substituent present, then it depends which shall uh, orientate this. So these rules are been constructed for that. Let's see, we have read the first this. If a strongly activating group competes with a weaker one, strongly activating, just look at on previous slide, which are strongly activating. We have strong activator when we have nitrogen, phosphorus, etc. Right? This is strong activator group. If you have oxygen, sulfur, nitrogen, phosphorus directly attached, this is a strong activating. If you have alkyl group, this is mild activating. If you have halogen, this is also mild. This is deactivator, not activator. So activator are those which are strong when you have a heteroatom directly attached. So not halogens, and alkyl group attached. So which are mild activators. So anyhow, if two of them are present, if a strongly activating group competes, strongly activating like this OH is a strongly activating group, competes with a weak one. Methyl, if you see, this is a mild activating, so we can say this is weaker than this entity, or a deactivating group. Let's say we don't have a methyl, but we have a deactivating versus activating group. And this is strongly activating, and if we are reacting with a deactivating group, the farmer controls the substitution. So farmer means strong activating. So strong activating group controls the orientation. It means this electrophile, now possibly if this methyl, we see this is ortho position is occupied, this is ortho and para. These two substitutions are also possible, but we don't get these product isolated because this OH in fact control this this substitution. If one ortho position is occupied, and then it can orientate this to this position and that position. So these two isomer number 2 and 3, they are isolated as well. So it confirms that OH group or any strongly activating group orientate it at these positions. I have exemplified another one. Here we have taken a strongly activating versus weak activating group. Here we have a competition between a strong activating versus a deactivating group. So nitro group is a deactivating group, right? So this is a just for your comparison. I have taken two options, weaker and deactivating one. So this is weaker activating, and this nitro is deactivating group. So this is, I have taken both example. So whenever we are bringing a new electrophile, whatsoever is the nature of electrophile, doesn't matter. This methoxy group now shall orientate this. So ortho position and para position. These two isomers are possible, isomer number 5 and isomer number 6. So this is the very first rule of orientation. Now let's see if I present I have presented when these two groups are ortho to each other. Maybe these two are meta to each other or they are para to each other. Let's see if we see in the next slide. This is the same you have seen in previous slides. If we have a isomer, two groups, one strong activating, other is weak activating or deactivating. Deactivating shall be silent. Either this is ortho, this is meta, this is para, shall not make any difference, but isomer shall be different definitely. If this methyl is in fact, both of these two are ortho, here they are meta, and here they are para to each other. Now let's see the electrophile, if approach, it shall approach definitely. You have seen this at this position or at that position because one ortho position is occupied. So two isomers are possible, both isomers are formed, but this isomer is formed in less concentration than that. Why? You shall see after this orientation another topic which we call steric factor. Steric factor means steric crowding. This OH group have two non-bonding electron pair. So it has a steric repulsive forces in her. As a result, this electrophile, if it is also sterically crowded or have some alkyl group, etc. attached, so it may have a steric hindrance with this. So due to steric hindrance, this ortho isomer or isomer number 3 shall be slightly minor. But look at here. This electrophile is present here. There is no steric crowding on either carbon. They are free. So this isomer shall dominate over this type of isomer. But if we have two groups present in this form, meta position, then the electrophile have three positions possible. This position, and that position. If we look at here, you shall see the next rule that electrophile doesn't approach between the two groups. Why? Because between the two groups, when you see, when this group is approached, this is approaching one side is steric crowding, other side there is no steric crowding, but this is also getting minor product. But if it is approaching between the two groups, both of them are sterically crowded. So let's say this electrophile shall be very hard to approach this, right? So this isomer we normally a very poor concentration. This is from negligibly poor. So that's why we exclude the possibility of this. You shall see the next rule is this one. So two isomers are possible. One is this one and other is this one. Both are forming. If you see here, electrophile is competing with methyl as a steric crowding. Here, this electrophile is competing with OH. Again, it is. So there is no major minor I have presented in this case. So because it depends upon if let's say we have this group, size of this will increases. This methyl changes to ethyl. It shall offer more steric hindrance. So this concentration of this shall decrease, it shall increase. If let's say I change this to isopropyl, which is sterically more crowded, then the percentage of this shall further decrease and that shall further increase. This is one I am increasing this concentration. So the steric crowding of this methyl I am increasing. So the percentage of 5 is decreasing, 6 is increasing. If I do the opposite, if I increase the size of this group, let's say I attach to oxygen methyl, now it shall be sterically more crowded. Concentration of 6 shall decrease, that of 5 increase, opposite, reverse effect. If I change this hydrogen by ethyl group, it is sterically more crowded than methyl. Again, concentration of 6 shall decrease and 5 shall increase. If we have, let's say, a benzyl group present here, or isopropyl group present here, that shall be sterically more crowded. So concentration of 6 shall be very small and that of 5 shall be very large. It all depends what is the steric size of these two groups. But electrophile shall not approach between the two entities. You shall see the next rule is this one. So, and the percentage of these two isomers depends upon the steric crowding of these two groups. Right. Finally, we have these two groups present. So para of this group is occupied. We have only two positions remaining. One is this one, other is this one. If you look at this position and that position, they are same because this oxygen, this position, ortho position have OH ortho and methyl meta. Look at this one. It also have ortho OH and meta methyl. So these two carbons are identical. Either electrophile approach this carbon or it approach this carbon. They are same molecules. So only one isomer is possible when there are two groups in fact. So you see only one isomer in this case, but in these two cases we have in this ortho position we have only two cases possible. In this one we have three possible, but only two of them are formed. So look at the next rule. The electrophile is least likely to approach between the two groups. This is the same I have presented in previous slide. So this rule says that the electrophile is least likely to approach between two groups due to steric factor positioned at meta. When two groups are positioned at meta position to each other, electrophile shall not approach between them. This one. This isomer is not possible. And if you remember, there are two groups. One is strongly activating, other is strongly deactivating. These are the two groups. So definitely this group shall dominate. So the groups I have presented in green color, they are dominating ones. So they are in fact causing orientation. The other one shall be receptor. So this group is dominating. So electrophile shall not approach between the two groups. This is the second rule. So what is the other possibilities? This is the ruling power. So it is orthopara director. So it shall orientate this electrophile at this position and at that position. So we shall get two isomer number 2 and isomer number 3. So this is another rule which is called second rule of orientation. So another rule which is also very important in this case, very important to understand what is this. When a meta-directing group are deactivating group, in other words, when a meta-directing or you can say a deactivating group is meta to ortho-para-directing. It may be strongly activating ortho-para-director or any other kind of ortho-para-director. The approaching electrophile is oriented at ortho to meta directing group. This is very important to see. We have two groups. One is a meta director or deactivating group. Other is activating. It may be mild activating or it may be a strongly activating. But you see, this is ortho para director we are using more broadly. It means to include halogen there, although they are deactivating. This is strongly deactivating, this is mild deactivating. But we have covered ortho para director, which are activator, as well as this broad terminology is ortho para directing, right? So if we have a meta director, if we have a ortho para director, meta to each other. Now, definitely this is activating, deactivating, but it deactivates small, it deactivates more. So theoretically, this should regulate. Electrophile shall not approach here. This is the previous rule that you have come across. What is the other possibility? One is this one, another is this one. Two isomers are possible. So let's see what I have presented here. All four isomers are possible with respect to this position, and this position is possible. I have presented this here at this position and para to this position. One position is also possible if let's say it is ruled by nitro. Nitro is meta director. This meta is occupied. This is the other meta I have presented. So this is against the rule number 1, if you remember. We have already said that if we are having a strongly deactivating group versus a mild deactivating shall control. If we have a deactivating versus strongly activating, then strongly activating controls. If we have a strongly activating versus mild activating, then strong activating controls. This is the pattern. So this is the violation of rule number 1. So that's why we shall neglect this one. It is not going to form in fact. So look at here. This is an electrophile approaching between the two groups which are meta to each other. So this isomer is also not going to form in this case. Thirdly, let's see, this is electrophile is approaching here, and this is approaching here. Now this is sterically less crowded, and this is sterically equally crowded. Nitro group and chlorine have a slightly less size. Nitro is having a slightly bigger size. So these are the two groups position. Now this rule presents the approaching electrophile is oriented at ortho to meta director. Ortho to meta director, which is this one. So it means this product shall be formed more rather this one. So this is the observation. It doesn't mean this is the always true. We may get this group indicating, let's say if this deactivating group is sterically very crowded, then the percentage of this shall decrease and this may be increased. It is normally when these two size groups are of normal size, equal size, steric factor is common, then this rule is been applied. But if there is a huge difference in their sizes, then it shall be different. So you shall see that in practice further. So these are the rules of the orientation. Now, in some other nuclei, what is the factor? Let's say orientation in naphthalene have two possibilities. In one case, electrophile can approach this position, which we call alpha position. If it is alpha position, you see it generates a positive charge here. If it is a positive charge, so then electron can be transferred here and it shall have a resonance form. It means this positive charge is stabilized by this double bond here, and this phenyl ring resonance energy is still intact. Although this phenyl ring is also stabilizing this charge here, but if it is just this double bond is stabilizing this, so this phenyl ring resonance energy is still intact. If it is intact, it shall be very stable. So this ion is more stable. Second ion, compound number 2, this is an intermediate, this is more stable. Let's say compare this with the other one. If I take the other possibility, this electrophile may also approach this because there are two positions possible. One, this one, this one, this one, this one, they are identical. Any position it can go that I have presented on one. On the other hand, this electrophile can approach this, and these two positions. These are called beta positions. So if it approach, let's say this one, so electrophile approach beta position. Now where is the positive charge? At this position. Now look at here, this positive charge shall be stabilized by these systems. If it is this pi electron density transfer, then the resonance energy of phenyl ring shall be destabilized. So it shall have higher energy, mean less stability. On the other hand, this double bond which was stabilizing this positive charge here is not stabilizing this one here. So that's why this ion or this intermediate, you can say, shall be of lower stability, or you can say high reactivity. So this is, if we are having kinetic condition, definitely this shall be dominating over this one. But if we are doing this reaction under thermodynamic condition in high temperature for longer duration, then this isomer shall dominate because it is having phenyl ring resonance energy intact here. This is not possible. So this is the possible that naphthalene is reacted under kinetic condition or thermodynamic condition. If it is kinetic condition, then beta product shall dominate. But if it is thermodynamic condition, then alpha product shall dominate over beta one. This is what we can present. Now let's see, I have presented another nucleus, phenanthrene. If we look at phenanthrene, electrophile, if you remember, these two positions are important. Either this one or that one, they are identical in fact. So in this case, it doesn't make any difference. This electrophile is approaching here or this is approaching there. In this case, if it is here, let's see. So you see this is stabilized by this phenyl ring and contributing by this one as well. Similarly here, so it doesn't make any difference in this case. Either it approach at this position or it approach at this position, because both positions are identical in fact. So this is all about the orientation. The other aspect I am interested to include is ortho-para ratio. Ortho-para ratio means what? You shall see right now. So this is called steric factor, in fact. So how to include this into this consideration? First of all, let's see, I have exemplified this. This is a structure number one. R group is variable. So I'm not defining the R at the moment. Just look at this structure. This electrophile approach, so there are three possibilities. Let's say we include that this R group is ortho-para director. This study is only for such groups which are ortho-para directors. If it is because we are studying the ortho-para ratio, because if a group is orientating any entity ortho-para, so this ortho, this is also ortho, this is para. So there are three possibilities. Out of these three, if this group approach here are there, they are same. So it means the chances of these two groups is higher than this one, right? So if let's say this is 2 times and this one, so total 3x, total 100%. So x shall be 100 by 3, which is 33%. It means 33% chances that electrophile is substituted here is this one, 33 this one, and 33 this one. So overall, if we look at either this electrophile approach, this position or that position, they are same isomers. So 33 and 33, 67. So this is theoretically I have present. Theoretically, 67 to 33 ratio is expected. Mean these two structure number 2 and 3, yes. Structure number 2 and structure number, if you look at, uh, this is ortho. Now, this structure is not the structure number 4 that is showing the meta direction, which is very impossible. So these two, either this electrophile is at this position or it is at this position. So these two groups, if present at these two positions, it have 33%, they are identical. But if it is at this position, this is structure number 3, which is para product. So ortho-para ratio, ortho 2 ratio 3. So this is 67 to 33 theoretical. But always we doesn't get the same ratio. Why we doesn't get the same ratio? This is due to the nature of the R group. Let's see. If this R group is halogen, if this R group is halogen, so we get para product dominating over ortho. This is very important. Look at this. If this is fluorine, we get 88% para product in this one, structure number 3. And structure number 2 is formed less. When fluorine is replaced by chlorine, so it is para percentage is decreasing, ortho is increasing. If it is bromine, then this increase is or decrease is logical. When this is iodine, we get 59% para and ortho is only 41%. Theoretically, it should be opposite. Dominating one should be ortho, but here it is opposite. Why this is opposite? This is opposite due to inductive effect. If you remember, if we are moving in this group above the plane, or let's say if we are moving from top to bottom, if you remember, fluorine is the most electronegative atom, most electronegative element. So it has highest electronegativity. So it has a highest effect when it is withdrawing electronic density. So due to it is having a minus I effect. When it is electron withdrawing, so these ortho carbons are electron deficient to some extent. Although due to resonance, which have a poor contribution, it is increasing slight negative charge here, slight negative charge here, and slight negative here. So this factor of electronegativity, the plus R group, resonance group is same. There is no change at all. But what is changed? Change is here. This group is far away from fluorine, having no effect of electronegativity. Either this is fluorine, chlorine, bromine, iodine shall have no effect on this. So that's why it is orientated sterically least crowded. But these two positions are under direct minus I effect of this R. More electronegative this one, you see this is producing less and this is produced higher one. So as we are moving down the group, electronegativity is decreasing. So this partial positive charge here is decreasing. That's why the percentage of ortho is increasing. So this is due to the minus I effect of this group present at this position. This is the one of the factors. Ortho-para ratio is one of the factors is dependent upon what is the electronegativity of this R group. This is electron withdrawing, so it shall be affected. If this is electron donating, let's say this is alkyl group, so this is alkyl group, it shall increase the electronic density at ortho. Ortho shall dominate over para. Now just look at here. We have reversed this. Now if this R group is alkyl group, let's say I have presented this R is methyl, ethyl, and propyl and isopropyl. All of these, if you look into this, these are electron donating, but they are electron donating. These are electron withdrawing by inductive effect. They are electron donating by inductive effect, opposite effect. They are increasing electronic density on ortho, but para has least effect, zero effect. So here electron density is slightly increased by this R. So you see ortho product is dominating over para. And this ratio is very close to this, but not exactly the same. So this is methyl. If I change this by ethyl, steric crowding is increased. So ortho product percentage shall decrease, para shall increase. Why? Due to steric factor right now. So N-propyl sterically more crowded than ethyl. You see ortho further decrease. When this is isopropyl sterically very crowded, it is just 17%. So it means this ortho-para ratio is dependent upon two factors. One, this group, if electron withdrawing, what is the electronegativity of that atom? This is one of the factors. Second, what is the steric factor of this group? So these are the two important aspects. If steric crowding, we are moving down the group. So you see the steric crowding is increasing. As steric crowding is increasing, the ortho percentage is decreasing and para percentage is increasing. So it has a totally opposite effect. Here electronegativity of this R group is present, so causing electron decrease due to electron withdrawing effect minus I effect. It is withdrawing electronic density from here, so ortho shall decrease, para shall increase. It is reversed. If this group is alkyl, if it is plus I group, electron donating group by inductive effect, they shall cause increase in here, but it is dependent upon the size as well. If it has a larger size, so definitely para shall be dominating over R. So these are the two effects that are very important in discussions of this. So these are a few rules that I have highlighted. The same I have been highlighted here, but less than 1 minute is